Okay, problem interrupted. Now, let's see where we're at. Okay, given sine x times sine x plus cosine x, and letting u be sine of x and v equals sine of x plus cosine x, f prime of x is going to be u prime, which is cosine x, correct? V, which is sine x plus cosine x. That's my u prime and my v, plus u, which is sine x, v prime, which is cosine x, going term by term, derivative of sine is cosine, plus negative sine x. That's my u v prime. Have I derived those two terms correctly?
Yeah.
Okay. Do a little distributing, and I'm going to get sine x cosine x plus cosine squared x plus sine x cosine x minus sine squared x. Oh, what's very frustrating about this? What am I frustrated about right now?
The sine x cosine x is not going away.
Yeah, the sine x cosine x is not going away. But you know, whenever I get close to a trig identity, if this were cosine squared x plus sine squared x, what would that be?
Oh, yeah.
Oh, but then it's still negative one. So.
No, they'd have to both be negative. They have to.
Yeah.
It has to be both the same sign. Good call though, but don't do that.
Okay.
All right. So whenever I see cosine squared and sine squared x and they're not the same sign, S-I-G-N, positive or negative, I always am like, oh, I could have had a trig identity. So I didn't quite leave myself enough room. This does become 2 sine x cosine x plus cosine squared x minus sine squared x. I don't see, without getting really crazy with trig identities, I don't see a good way to simplify that. I don't think the answer would be any simpler. Now looking at this one. All right. Never happy with my marker. Potentially tricky one here. I'm going to give you guys a hint that I want you to start doing in your head. I'm going to rewrite sine squared x as sine x whole thing squared. What's the advantage to that?
You can just, visually it helps to remember that the squared goes to the x, to the whole value of sine x and not just like sine.
Excellent, very good. But that visually what that helps you remember is that I have to use a certain rule. One involving inside and outside functions.
Yeah.
Which rule is that?
U substitution.
U substitution is when you're anti-deriving.
The chain rule.
The chain rule, yes. If I write, when kids see it like this, they don't always remember this is a chain rule situation, but as you put it so well, Jen, when you clearly distinguish that the sine x, the squared goes to the sine x, in other words, that you have an inside and outside function situation, it can be easier to see that when you take the derivative, your outside function is x squared, so you apply the powers rule. Bring down the 2. Does the inside function change in this step? I'll take that as a correct answer of no, the inside function does not change at this step. So I get 2 sine x to the first times the derivative of the inside function. What's the derivative of sine? Cosine x. Plus, no way around it, have to use the product rule here since we didn't use it up there. So we have to use the product rule between sine and cosine. U is sine, so u prime is cosine. U prime v becomes cosine cosine plus u v prime, derivative of cosine, is negative sine x. And can you see in another moment we'd have 2 sine x cosine x plus cosine squared minus sine squared. We'd have the exact same answer as up above.
Oh.
Okay.
So this one's very straightforward without using any fancy trig identities or
How?
anything else.
Possible.
if we don't distribute, we use the product rule with u as sine x and v as sine x plus cosine x. And when we're done simplifying, we get 2 sine x cosine x plus cosine squared minus sine squared. If we do distribute, we have to remember to use the chain rule on sine squared, sine of x, whole thing squared. And then we get 2 sine x cosine x. Cosine x here appears because it's the derivative of the inside function. Plus, we apply the product rule on sine x cosine x, and that gets us cosine squared minus sine squared. Exact same thing we get that way.
Do things like that happen in other times?
All the time. I mean, if you take the derivative of anything, what's going to happen here is you're going to start getting, it's going to be a judgment call or even a personal preference. This is not a case where I can say, okay, your strategy should be to use this sometimes, that sometimes. This is going to be like, what do you prefer? In which case are you more likely to get the algebra correct? But you should always get the same answer or something you can prove is the same answer. This one's pretty straightforward. Where it's a pain in the butt is when you, as you guys have been noticing, those who've been checking the answers in the back of the book lately, you get an answer, your answer's correct, it looks nothing like the back of the book because of the algebra steps required between what you did and what the book did. Or you chose one setup and the book chose another. Or you chose one setup and the Advanced Placement College Board has some set of multiple choice answers that assume you did a different setup. So there will be cases where you'll have to use algebra steps, trig identities, something to show that, like, to figure out that the answer you have is the one you want. In real life, if you're an engineer using a derivative to actually solve a problem, to figure out the instantaneous speed of an object or some other rate of change, you usually don't care what final answer you get because you're about to plug a number in, and that should always get you the same answer. But for passing this advanced placement exam, you need to be able to get an answer and see how you can change it into other answers.
So you sort of treated it almost like 2 separate problems there, but adding them together. Yeah. So like for the first one you did the chain rule, and the second one you did the product rule.
Close. For the first one I did the chain rule.
No, I don't even mean that. I mean
just down here?
Yeah.
Yes, here, yeah. I treat it as I treat each term separately. Remember, limits can be distributed across terms.
Yeah.
So, unlike everything else, I keep saying it. Remember last year in pre-calculus, I could say you can't ever distribute anything across terms. Well, limits are the exception. Limits you can distribute across terms, which means you can take the derivative of sine squared x, just do this as a chain rule problem, just do this as a product rule problem. And now let me do one more of those, and I'll do one more trig one, and then I do want to get to an algebra one. Tyler, can you follow me over this way?
Yeah.
Excellent. Can you see what I'm writing?
Yeah, through the camera.
Okay, good. Okay, what's the first rule you should think of looking at this situation? Chain rule. I got an inside function and an outside function. My outside function is x cubed. My inside function, tangent plus secant.
3
It's the worst apostrophe I've written in years of teaching.
Wait, isn't it an apostrophe or is
parentheses
it
tan
really?
x plus sec x.
Squared.
Yeah.
And then what?
Sec x. Wait,
Secant squared.
yeah, sec squared x.
Secant squared x. Good. The derivative of tangent is secant squared.
Tangent, secant.
Very good. Plus tangent x secant x, because the derivative of secant x is tangent x secant x. I wouldn't particularly try to simplify this. I'd hate to think what the back of your book would do with it, but this is where I would leave it.
Wait, but yeah, if we factor secant x out of the second
Out of both terms, yeah.
yeah, so then we could make Wait, without.
Oh my good lord, yes, hang on, Joey, you're right, the back of the book would do something, I missed something obvious. Tangent plus secant x squared times secant x factored out of this, leaving me secant x plus tangent x, correct?
Yep.
So the back of the book would have 3 tangent x plus secant x cubed, these are the same factor, times secant x. And they probably moved this through secant x next to the 3. Good eye, Joey.
Wait,
That doesn't
but,
usually happen. That's tangent plus secant is kind of a unique
but there's 2 tan x's and 3 sec x's. So how is it?
Okay, secant squared plus tangent secant, right? I factor a secant out of each term. So in what's in this bracket is this part here. And all I've done is factor out a secant.
Yeah.
And now I've just got 3 things multiplied by themselves. Well, 4 including the 3. I've got tangent plus secant squared times tangent plus secant to the first. So that's going to give me tangent plus secant cubed.
Oh, okay.
And leave that secant all by its lonesome outside. Tangent plus secant is in, I think I had in my mind something I'm going to teach you later about tangent plus secant, how it does sort of show up in its own derivative a lot. That's one of the signs you're in a transcendental function is either on the first derivative or after multiple derivatives, they tend to show up again as you derive them. Joey, to answer your notational question, is it an apostrophe or a Roman numeral? It's an apostrophe for the first 3 derivatives, and then some books change it to Roman numerals starting with the 4th derivative. But you almost never get to the 4th
That's
derivative.
irritating.
That is irritating. Well, I've already talked about my hatred of other notational inconsistencies. There is algebra in the homework tonight, so let's do at least one algebra example. All right, Tyler, follow me back to the other board. By algebra, I mean polynomial, as opposed to trigonometry. So those are really the only 2 things we've looked at. Well, no, that's not true. We've looked at fractional exponents and roots as well, but they just follow the polynomial rules in this case. Never actually proved that. With binomial expansion, we proved why the powers rule works for polynomials, and then I just said, take my word for it, it also works for fractional exponents and roots. All right, which one of these is slightly more or less irritating? All right, that'll work. New example. Find the equation of the tangent line to f of x equals, I'll pull this example out because it's similar to the homework, x minus 1 over x plus 1. Now if you're asked to find the equation of a tangent line, just giving you the function isn't enough because this function has an infinite number of tangent lines always touching it somewhere. The last one, so I have to say at the point 2, 1/3. Quick double check, is that point really on this graph? I put in 2 for x, 2 minus 1 is 1, 2 plus 1 is 3, y does equal 1/3. Okay, so we need the equation of this tangent line. I'm going to kind of steamroll through this one because of time, but, well, I'll ask you this, what rule do I need to use? Quotient rule. I'm staring at a quotient. You need to use the quotient rule. Joey, what is the quotient rule?
Okay, u prime v minus v prime.
uv prime, yep.
Prime over v squared.
Jen, is it v squared or v prime squared on the bottom?
squared.
V squared, excellent. Okay, so f prime of x equals u prime v. I'm going to do this without writing out the u's and the v's because I've just got simple binomials, everything's first degree. Derivative of x minus 1 is just going to be 1. So it's going to be 1 minus 0, but forgive me if I just write 1 there. V is x plus 1 minus u, which is x minus 1, times v prime, derivative of x plus 1 is again just 1, all over x plus 1 squared. Did I keep track of my pluses and minuses correctly? I was honestly a little worried about that. Prime v, it's on the bottom, uv prime, u, the one on the top, x plus 1's on the bottom, v squared. Any questions so far? Help if I write the u prime, the v, the u, the v prime, and the v there. As I do that to double check. 1 times x plus 1 is x plus 1. 1 times x minus 1 is x minus 1. X plus 1 minus x minus 1. X minus x is 0. 1 minus negative 1 is 1 plus 1, so that's 2 over x plus 1 squared. I found the derivative. Am I done?
No, now we need to find the
Equation of the tangent line. And we do. So to find the equation of the tangent line, we're looking for the slope of the line that touches this graph at this point. Another way to say that is we're looking for f prime of 2. Take this x value, plug it in here to the derivative, and that means 2 over 2 plus 1 squared, which is 2 over 3 squared, which is 2/9. So that's my slope of my tangent line. They didn't specify a format for this line, but
point slope
point slope is almost always the least work in this case. So y minus 1/3 equals 2/9 x minus 2. Only possible extra work you would have is if you're staring at a set of multiple choice answers and they're all in slope intercept form.
Can we do it to y equals mx plus b form?
Yeah. In fact, sometimes what I like to do is do this first, and then I make it y minus 1/3 equals 2/9 x minus 4/9. And then I add 1/3 to both sides. 1/3 being 3/9, that's 4. Okay, so that should be y equals 2/9 x minus 1/3, I think. So I'm going to add 3/9 to both sides.
Oh yeah.
Wait. Okay. So you're getting
Wait, no,
one?
minus
I don't get how you-
1/9.
Where are you getting the
Minus 1/9, thank you. I added 1/3 to both sides after I distributed the slope to the x and the 2. But the key thing is, Jen, is you'll get a question like this on the AP, and you really have to be able to recognize either this or this as one of the multiple choice answers.
And what form is points? What's point slope? It's y minus.
Y minus y sub 1
Yeah.
equals slope times x minus x sub 1, where the letters without the subscripts are your actual variables, and x sub 1 and y sub 1 are a known point. Random last thought of the day on an interesting real-life application of this to something going on right now, and I'm going to give you this without putting any of my opinions into what I'm about to say, which is actually very hard for me, but I'll try. Tyler, follow me over here for a sec. There are many ways to measure the performance of an economy. There is your gross national product, how much money is being generated by the economy. There is your unemployment rate. Currently, we have an economy that is not doing well, this being 2012, and we're recovering from a major systemic crash of our economy in 2008. We also currently have a presidential election, and one thing that startles some people about this presidential election is how close it is at this point, or the fact that the incumbent has a slight lead in most polls, because in a lousy economy, that usually favors the challenger. Bad economies, the challenger tends to get booted out. So for example, if you look at unemployment right now, let's say unemployment right now is somewhere around like 8%, I think. Here's this point on a graph, it's 2012. If you look at other years when unemployment's been anywhere near this, the incumbent usually does poorly and often loses the election. Almost always. There's many other things. You look at gross domestic product. But somebody finally did something smart. Like here's a graph of unemployment in America right now. Apparently it looks something like that. That's not an exact graph.
You think it's going to go down
It is currently in the process of going down very slowly. The economy is net adding jobs. So if you just look at the unemployment number, you would say the incumbent's in trouble. But somebody finally did something very smart, or people have been doing it, but somebody finally started writing about something very interesting. They didn't start looking at the unemployment, they started looking at the slope of the tangent line to the unemployment, the rate of change, and also to other factors, like how many jobs are being added to the economy. If you look at the number on this graph, okay, you would say, oh my God, presidents with this number never do this well in polls. But if you look at the rates of change, the slope of the tangent line, in other words, the derivative of whatever equation is sort of modeling this, then you see a negative slope, which means unemployment is decreasing. And what someone did is finally look at the rates of change of unemployment at this point in elections, and the polls actually match up pretty well. Incumbents do well as long as things like unemployment are going down, and right now the economy is not producing a lot of jobs or money. It's a very low number, but it is going up slightly, and incumbents often do well. So you need to look at the derivative, not just the number. Does that make sense? For super quick applied. That's what we're doing, yes sir?
I mean, doesn't how the change in the unemployment rate is perceived, isn't that more important
Yes.
than how it actually is changing?
And that's an interesting question. I don't know. Yes, to short answer to a voter, yes. But apparently from what I've read, though I may have to go back and double check this, the perceptions nationwide, and if you poll enough people and are careful to do your poll scientifically, the perception usually tends to match the reality of how many people are finding jobs. So the magic number is actually a rate of change. It's actually a derivative. I think it's if the economy adds more than 150,000 jobs a month, the incumbent's usually a shoo-in. And we're a little below that, so that's part of what's making it a close range. So by the number, the challenger should win. By the derivative, the incumbent should stay in office. That's part of what makes this election a bit more of a toss-up than most. But economic indicators are often a very good idea. All right, that's it.